computer. All right, and Mr. Joyner apparently doesn't record himself all that often. That's your name, right? Yeah, yeah. You're photo bombing, aren't you? Something like that. Okay, all right. So we're recording, and see what I'm doing for you guys. This is illegal, by the way. They don't like us doing this anymore. Let's see. Huh? Yeah, but it's gonna be our little secret, okay? Huh? Oh, shit, yeah, it is. All right, so let me go back to my whiteboard. I just cursed on YouTube. They won't, they're gonna.
Might get flagged.
I'm gonna get flagged. They're gonna take it down. They're gonna take the video down. Oh, okay, all right. Okay, so guys, I'm gonna go back to the bread analogy just so you guys can see this. Okay, so I have 10 sandwiches, and I asked you for how many slices of bread. You guys said if I had 10 sandwiches, I'd have 20 slices of bread. The way we do this, even though you guys worked it in your head rather quickly, I might add, you said we have 2 slices of bread for every sandwich. So I have write my given down, my 10 sandwiches, and then of course I'm going to do some little bit of dimensional analysis, if you will. I'm going to multiply it by 2 slices of bread divided by 1 sandwich, and of course slices of sandwiches cancel out. I have sandwiches in the numerator of my given, sandwiches in the denominator of my conversion factor, and I'm going to use the red ink pen. Pow. See how sandwiches cancel out? And I'm going to multiply 10 by 2 and divide by 1, and I'm going to end up with 2 slices of bread. So I'm going to do the same thing with ethane. The problem, of course, as it says, according to the equation below, how many moles of carbon dioxide are produced, starting with 3.43 moles of ethane. So I'm going to take my given 3.43 moles of ethane, and I think I'm going to go ahead and get rid of that because it's, all right. And what the hell? Okay. All right, so I'm going to take my 3.43 moles of ethane, okay, and I'm trying to get moles of carbon dioxide, okay? It doesn't matter if it's a product or it's reactant. If I ask you how much of a reactant I'm going to have to react with it, you do it the exact same way, okay? So in this case, carbon dioxide is a product. I'm going to have 4 moles of carbon dioxide formed for every 2 moles of ethane that reacts. So I'm going to take 3.43 moles of ethane times 4 moles of carbon dioxide divided by 2 moles of ethane. Let's see. 3.43 times 4 divided by 2, that's equal to what? 6.86 moles of CO2. All right. So you guys with me so far? All right. Now you're going to have to do this, okay, when you do stoichiometry. I mean, when you do a full stoichiometry problem. Now, a full stoichiometry problem, they start off with grams. You have to convert the grams to moles, do the stoichiometry, and then convert the moles back to products. So had this been a full stoichiometry problem, I would have given you grams of ethane and asked you for grams of carbon dioxide. You guys follow me? So you use the molar mass of ethane, which I would have provided for you, and then you convert the grams to moles, do the stoichiometry, and then you convert the moles of carbon dioxide to grams of carbon dioxide. You guys follow me? All right. Okay. So let's go ahead and clear that bad boy. Okay. What the hell? Oh, is hell considered a curse word? Oh. Huh? Okay. All right. Yeah, I don't think I'm going to be a good YouTuber. Okay, so number 2 says aluminum reacts with oxygen to produce alumina according to the equation. 4 aluminums plus 3 oxygens yields 2 aluminums. Okay, all right. So how many moles of O2 are needed to completely react with 7.97 moles of aluminum? Now, of course, I don't have time for you guys to do this problem, but while I'm doing my full screen step, why don't you guys try to take a crack at it? If you can work quickly, that would be awesome. La, da, da, da. La, da, da, da. Da, 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 Ta. Okay. All right, so let me read this bad boy again. Aluminum reacts with oxygen gas to produce alumina according to the reaction. So notice that I have 4 moles of aluminum reacts with 3 moles of oxygen to produce 2 moles of alumina. How many moles of oxygen are needed to completely react with 7.97 moles of aluminum? Now notice they gave you the moles of one reactant and they asked you to find the moles of the other reactant. Okay, this is something that we have to do all the time in chemistry. Okay, we have to do this all the time. The other problem, they gave you moles of reactant and they asked you for moles of product, which is something else we had to do. So technically, we found the theoretical yield in moles. When you find the theoretical yield, most of the time you find it in grams. But for problem number 1, we found the theoretical yield in moles. Okay, so this is a simple matter because I'm going to have moles of aluminum. They asked me for moles of oxygen. So of course, I'm going to multiply by 4 and divide by what? Divide by what? 2. No, guys, they gave you moles of aluminum and they asked you for moles of oxygen. So I'm multiplying by what and dividing by what? Multiplying by 4 and dividing by what? 3, right? Because they asked you for oxygen. They didn't ask you for alumina, they asked you for oxygen. Y'all with me? Okay, all right. So I'm going to say 7.97 moles of aluminum times 3 moles of O2 divided by 4 moles of aluminum. Notice that moles of aluminum cancel out. I got moles of aluminum in the numerator of my given and in the denominator of my conversion factor. So I'll say 7.97 times 3 divided into 4 equal parts. And I end up with 5.98 moles of O2. Now again, had this been a full stoichiometry problem, they wouldn't have given you moles of aluminum. They would have given you grams of aluminum. You would have had to convert the grams to moles, do the stoichiometry, get the moles of oxygen, then convert the moles of oxygen to grams of oxygen. That would be your theoretical yield. Not theoretical yield, but that's how much oxygen you need to react this. No, you use molar mass. Use the molar mass. The molar mass for O2, for example. If I have 1 oxygen, it's 16. Okay, so if I have 2 oxygen, which I have in that molecule right there, it's going to be 32. So 32 grams is equal to 1 mole. And if I have moles, and I know 32 grams is equal to 1 mole, I just take this number and multiply it by 32 grams divided by 1 mole, and I have my answer. Okay, all right, you guys with me? Okay, so let's go ahead and let's see. There was what number was that? 2. Okay, so number 3. Aluminum reacts with oxygen gas to produce alumina. Okay, so deja vu, right? According to the equation, 4 aluminums plus 3 oxygens plus 2 alumina. Okay, how many moles of alumina are produced theoretically, starting with 8.44 moles of oxygen and in excess of aluminum? Okay, so now they're asking you for alumina. So they give you moles of oxygen and they're asking you for moles of alumina. So I'm going to take this 8.44 moles of O2 and multiply it by what and divide it by what? Okay, they're asking you, they give you moles of oxygen, and they ask you to find moles of alumina. So if I have moles of oxygen, which is 8.44 moles, what number am I going to multiply? Huh? Multiply by what? Why divide by 4? Divided by 3. Why 3? They give you O2. These are moles of O2. Okay, all right. So y'all with me? Okay. All right. So do y'all need me to do this problem? Okay, we don't have enough time, guys. I'm trying to get through all of these. Huh? Okay. So what the hell? Oh. No. All right. Let me see. Yes, do it right there. Let me. That's the only downside when it comes to active learning, that you don't. Yeah. Miss Mathis. Do I still need to record this? Okay, I'll record it. You guys can look over the lecture over the weekend. Okay. Well, you can tell me if this helps. All right. So aluminum reacts with oxygen gas to produce alumina according to the equation. 4 aluminums plus 3 O2 plus 2 alumina. Okay, how many moles of alumina are produced theoretically? So I'm going to have 8.44 moles of O2. All right, times, let's see. So I'm trying to get moles of alumina, so I'm going to say 2 moles of Al2O3 for every 3 moles of O2, right? So I'm going to multiply by 2, divide by 3. Of course, that's 2/3, which is 0.666666667. All right, so 8.44 times 2 divided by 3. I end up with 5.63 moles of Al2O3 because moles of oxygen cancel out. Y'all see how I'm doing this, right? So like I said, in an actual, a full stoichiometry problem, they would not give you moles of oxygen, they would give you grams of oxygen. You'd have to convert grams to moles, do the stoichiometry, get the moles of alumina, then convert moles of alumina to grams of alumina. Okay, that would be a full stoichiometry. In that the grams of alumina, that would be your theoretical yield. Okay, that's how much you're supposed to get theoretically. Okay. All right. So let me. All right. So now we have our full stoichiometry problem right here. Full stoichiometry. All right. So let me go ahead and do this, my screen snip right here. Notice what I did. I provided you with the molar masses that you need to do the problem, didn't I? But yeah, by the way, guys, for some strange reason, they invited me to go to the International Women's History Month luncheon today. Yeah, the food was amazing. Yeah, I went. The food was, yeah, it was pretty good. I'm just saying. Yeah. So like according to the equation above, the mass of aluminum is what mass of aluminum is needed. So we want to end up with aluminum, right? Is needed to completely react with 108.65 grams of hydrochloric acid. Okay, they give you the molar mass of hydrochloric acid is 36.4609. They give you the atomic mass of aluminum, which is 26.982. All right. So the first thing I want to do before I can do the stoichiometry, I'm going to have to convert grams of HCl to moles of HCl, right? So I'm going to go ahead and say 108.65 grams of HCl. Okay. Now notice I have grams. I want moles. Okay. This molar mass, I have 36.4609 grams is equal to 1 mole. What am I going to put in the numerator of the conversion factor? What am I going to put in the denominator? 36.4609 grams, right? Okay, y'all with me? All right. You had a question? No. Okay. One? Because I'm trying to I'm trying to convert this to moles. That's the only way I can do the stoichiometry. You can't do stoichiometry with grams. You have to convert your grams to moles. If they give you moles, fine. So I'm going to say 1 mole for every 36.4609 grams. So let's see how many 108.65 divided into 36.4609. That's going to give me 2.97990 moles. Okay, don't truncate, don't round to the correct number of significant digits yet. Wait till we get to the end. Okay. All right, so now I'm going to have 2.97990 moles of HCl. Now let's see, what are we trying to get? They say according to the equation, what mass of aluminum is needed to react with this HCl. So I have HCl and I'm trying to get aluminum. Okay, so I'm going to multiply by what and divide by what? I'm going to multiply by 6. You sure about that? I'm trying to get moles of aluminum. Yeah, multiply by 2, divide by 6. Okay. As you guys, I'm sure you've noticed, I'm using my units. The sky is not falling and the world is not coming to an end. No, yeah. So moles of HCl cancel out, right? Okay, so I'm going to say 2.97990 times 2 divided by 6. That is equal to 0.9933 moles of aluminum. Okay, so let's go ahead. And now, of course, I have to convert my moles of aluminum to grams of aluminum. 0.9933 moles of aluminum times, let's see what the atomic mass of aluminum is. It's 26.982 grams is equal to 1 mole. So what am I going to put in the numerator? And what am I going to put in the denominator of this conversion factor? Huh? So I'm trying to convert moles to grams. So what am I going to put in the numerator, guys? That's what I'm talking about. 26.982 grams. I'm going to put 1 mole. That's what I'm talking about. All right. So I end up with 0.9933 times 26.982. All right. And that now this is my final answer, and it's good to how many significant digits? 1, 2, 3, 4, 5. Apparently it is good to 5 significant digits. So I'm going to say 26.801 grams of aluminum. So guys, if I had, let's see, 108.65 grams of hydrochloric acid, okay, and I wanted to do this reaction in the lab, I would measure out 26.801 grams of aluminum to react with it, okay? So you guys know you know the basics of doing chemistry. So when you do chemistry, you have to do your stoichiometry first. Figure out how much of each reagent you want to react with each. You guys know how to do this. This is the basics. So you guys can consider yourself third-ranked chemists. Okay, all right, so we get there, right? Okay, yeah, this is chemistry, guys. You cannot do chemistry if you can't do stoichiometry, okay? So, like I said, this is probably the most important thing you're going to learn in this class, all right? Stoichiometry, all right? All right, so we know how to do 4. What was the answer to number 4? Okay, so C, the answer is C. And why do I only have this reported to 3 significant digits if it's good to 5? Okay, I'll change that. If I can remember, I'll change that. Okay, now this is the limiting reagent problem, so we're kind of rushed for time, so I can only do one of them. You want me to do, I can either do 5, 6, 7, 8, 9, or I can do 10 and 11. Oh, well, no, it's because I asked you for moles of ENO, grams of ENO, moles of water, and grams of water. So, yeah. You do that one? Okay, I'll do this one. The one that takes more time. That's the one you want me to do. Thanks for suggesting that. Right? Okay, ammonia reacts with diatomic oxygen to form nitric oxide and water vapor. Okay, so we have ammonia reacting with oxygen to form. I'm assuming this happens at elevated temperatures. All right, so so when 20 grams of ammonia and 50 grams of oxygen are allowed to react, okay, they ask what is the limiting reagent, how many moles of NO are produced, how many grams of NO are produced, how many moles of water, and how many grams of water. So let me go ahead and do my full screen step. And yeah, that took an inordinate amount of time now, didn't it? Okay. All right, so I'm going to go back to my analogy. And I'm going to copy that. Okay, and I copy that and I go to my whiteboard. Okay, clear canvas. And let's see, hit paste. All right. All right, so going back to my sandwich analogy. Okay, now this time I got 3 slices of turkey per sandwich. Okay, 3 slices of turkey and 2 slices of bread. Okay, all right, that's what I have per sandwich, right? Y'all with me? Okay, it's not a very tasty sandwich, okay? I guess if you fried the turkey in, like, I don't know, coconut oil, it would make it a lot tastier maybe, but mayo, I hate mayonnaise, man. I don't do mayonnaise. You know, we're not getting down like that. No, no. Okay, all right. So now let's say I had 21 slices of turkey. And let's see, 8 slices of bread. All right. And I ask you, how many sandwiches can I make? No. 4. 4. Okay. So, all right. So so is it the bread or the turkey that limits the number of sandwiches? Bread. It's the bread. So the bread is the limiting reagent. Okay. So let's go ahead and show you this. I'm going to say 21 slices of 21 slices turkey times 1 sandwich per 3 slices. Okay, that's going to give me 7 sandwiches, right? Okay, then I'm going to do the same thing with the bread. I'm going to say 8 slices bread times 1 sandwich per 2 slices. That's going to give me what? 4 sandwiches. All right, so I figured out how many sandwiches I could get from the turkey and how many sandwiches I could get from the bread, and all I had to do was pick the smaller number. That's all I had to do. 4, I'm going to make 4 slices. I got it from the bread, of course, so the bread is the limiting reagent. We're going to do the same thing in this problem. Okay, we're going to do the exact same thing. So let's go down here. Let's go down here. All right, so I'm going to do the problem above it. Okay, so they give you 20 grams of ammonia and 50 grams of oxygen. Of course, the first thing I'm going to do is I'm going to convert my grams of ammonia to moles of ammonia, do my stoichiometry. Now I can either do the stoichiometry with the NO or the water. You guys take a pick. Which one would you like me to do? The NO or the water? It doesn't matter. NO. So, but if I do the NO with ammonia, I have to do the NO with oxygen too. Okay, so I'm going to say 20 grams of NH3. I left the other 0 off. It doesn't matter. Times 1 mole per 17.031 grams. Y'all see where I got this 17.031, right? It's 17.031 grams is equal to 1 mole. That's what I should have that down there. Okay. And so I put 1 mole in the top and 17.031 grams in the bottom in the denominator. So grams will cancel out. I take 20 divided into 17.031 equal parts, and I get 1.1743 moles of NH3. All right. And I'm going to say multiply that. So now it's stoichiometry time. I'm going to go ahead and do the stoichiometry. Did y'all say y'all wanted me to use NO or H2O? So I'm going to have 4 moles of NO for every 4 moles of NH3. All right, of course, you're going to multiply by 4, divide by 4, you're going to end up with the same number. That's going to be 1.17433 moles of NO. So I'm going to do the same thing for oxygen. We have 50 grams of oxygen. I'm going to have 50.0 grams of O2 times 1 mole divided by 17.0, divided by 31.9988 grams. That's going to give me 50 divided into 31.9988 grams. That's going to give me 1.56256 moles of O2 times. Now notice I get 4 moles of NO for every 5 moles of O2 consumed. Okay, so I'm going to take that 1.565256 times 4 divided into 5. I end up with 1.25005 moles of NO. Which one of those two numbers is smaller? The first one, 1.17433. Okay, all right, y'all see that? Okay, so what is my limiting reagent? Is it ammonia or is it oxygen? It's ammonia. Ammonia is my limiting reagent. Okay, so ammonia is my limiting reagent, so I know when I go back to, let me see. What the hell? Oh, okay, so they asked for the limiting reagent, you know, it's ammonia, then they asked for how many moles of NO are produced. We just found it. All we got to do is pick the smaller number. 1.17 moles of NO produced, right? 1.17 moles of NO. As far as I'm concerned, we could care less about this calculation now because we found the limiting reagent. So since I know the moles of NO, I can go ahead and find the grams of NO. In order to do that, I'm going to take the moles of NO times the molar mass of NO, which I don't know, but let's see what it has up here. It's 30.0061 grams is equal to 1 mole. All right, y'all with me? Yes, sir. Okay, all right. So 30.0061 grams is equal to 1 mole. And all right, I'm in a rush. I hope you guys will forgive the horrible way I'm writing that. Times 30.0061. That's going to give you 35.237 grams of NO. So that's the grams of NO that you're going to produce, right? 35.237 grams of NO. Y'all see how I got that? All right. No, I got moles of NO and I multiplied by the molar mass of NO to get grams of NO. Okay, so yeah, all right. Now sometimes we do this in chemistry too. We'll have an excess of one reagent. Okay, all right, but we'll already know that we're putting in an excess. All right, so if it's a cheap reagent, if one reagent is expensive, one reagent is cheap, they'll put an excess of the cheap reagent, drive the reaction to the right. It happens. Okay, so we know moles of NO, grams of NO. Now we have to get moles of water and grams of water. So now I know that ammonia is my limiting reagent, and I know that I have 1.17433 moles of ammonia. So it's simple to take 1.17433 moles of ammonia. But this time I'm going to do my stoichiometry with water. So if you guys recall, I formed 6 moles of water for every 4 moles of ammonia that's consumed. So I'm going to take my moles of ammonia and multiply it by what and divide it by what? Huh? Oh, okay. Yeah, multiply by 6 divided by 4. All right, y'all see that? Y'all see that, right? Okay, all right, because I'm trying to get moles of water now. So I'm going to multiply by 6 and divide by 4. So I'm going to say 6 moles of H2O divided by, what did I say I was going to divide by? 4, okay. 4 moles of NH3. All right. 1.17433 times 6 divided by 4. I end up with 1.7615 moles of H2O. Y'all with me? Y'all with me? Okay. All right. All right. Well, does it have to be a certain format you upload it on YouTube? I mean, can it be MP4 or does it can be like? It doesn't matter. Okay. Right. Okay, so let me see. The molar mass of water is 18.0153, okay, grams per mole. So I'm going to multiply that times 18.0153 grams per 1 mole. I mean, I have uploaded the video. I uploaded the video once before, but it was so long ago. It was like years ago. So yeah, I end up with 31.7340 grams of H2O. All right. So that's limiting the agent stoichiometry problem. And let's see. All right. Let's try to put all of this up here. And yeah, I guess you can't see it if I put all of it up there, can you? Okay, well, let's see that part. I'm all over the place because I sort of worked up, didn't I? Okay, but if y'all can forgive that, then I guess you'll get that. But yeah, all right, so let's see. Let's see, I got 8 minutes left. All right, so it says number 12, the reaction below. I have, let's see, that's ferric oxide plus 3 moles of carbon monoxide yields 2 moles of iron and 3 moles of carbon dioxide. I didn't know this was a thing. Okay, ferric oxide, that's rust, by the way. So apparently you can take rust and react it with carbon monoxide at elevated temperatures, and you can reduce the iron in the rust back to iron. Apparently that's a thing. Okay, yeah, I guess I'll never be a metallurgist, but yeah, but this reaction garnered 3.43 grams of actual yield of iron. Okay, the theoretical yield, okay, had they done the stoichiometry, the full stoichiometry, they should have gotten 3.97 grams of iron. Okay, but they only got 3.43 grams. So they want to know what the percent yield is. Okay, so of course, you guys know all you got to do is percent yield, you take actual yield divided by theoretical times 100%, right? So I'm going to say 3.43 grams divided into 3.97 grams times 100%. Okay, so 3.43 divided into 3.97 times 100% is equal to 86 point, how many significant digits? Yes, it's only got the 86.4% yield. Okay, now this particular reaction, you probably get quantitative yield. Okay, anytime you say quantitative yield, that means you're getting 100% yield. You get 100% yield for this reaction. There are no side reactions that are competing. Okay, so you're going to get all of the iron. So yeah, this is going to be quantitative. But in organic chemistry, those are reactions where you have a lot of side reactions. Okay, but so it's 86.4, and it's going to be C, right? Okay, y'all see that? Okay, guys, this is free 5 points, right? 5 or 6 points. How many points I make this, right? Nobody's going to get this wrong. Nobody here is going to get this problem wrong on the test, right? Okay. Guys, if y'all get that wrong, I'm gonna talk about you. I'm gonna talk about you some often. Okay? Okay, all right, so let's see. Number 13, assume you dissolve 0.395 grams of potassium permanganate in enough water to give a solution of 250 milliliters. What is the molar concentration of potassium permanganate? Remember, we're talking about molarity. Molarity has units of moles of solute per liter of the entire solution. They're saying the entire solution has a volume of 250 milliliters. Okay, so the first thing we want to do is we want to know how many liters that is. How many liters associated with 250 milliliters, guys? Okay, 0.250. But we also need, notice that they didn't give us moles of potassium permanganate. They gave us grams. So we need to convert grams to moles, don't we? And I'm surprised I didn't put that up there. When I repost this, because I'm going to repost it later on tonight, I'll put the molar mass of potassium permanganate, because I have to calculate the molar mass of potassium permanganate. Can somebody look up the molar mass of potassium permanganate? Just put molar mass of potassium permanganate. Somebody in Google, tell me what it is. I'll take y'all post some time. Okay. 158.034 grams is equal to 1 mole for KMnO4. Okay, all right, so we got the molar mass there, all right? And let's see, how am I doing on time? How much time do I have? I only got 3 minutes left. Huh? No, I didn't take roll. Why are you oh my God in me? Why are you oh my goshing me? Okay, so I'm going to say 0.395 grams, okay, times, I want to convert this to moles. So what I'm going to put in the numerator and what I'm going to put in the denominator. Yeah, guys, this was a trick question. 1 mole and 158.034 grams go in the denominator. So I'm going to take 0.395. If you want to multiply it by 1, you can, but it's not going to make a difference. But divide by 158.034, that's going to give you 0.00249946 moles of KMnO4. Okay, so of course, molarity is moles of solute per liter of solution. So all I have to do now is get these moles, 0.00249946 moles, divided by 0.250 liters, right? Y'all with me? Divided by 0.250, and I have a molarity of 9.99785 times 10 to the -3. Notice that this is a capital M. That's what we use for molarity. Now, of course, let me see how many significant digits this bad boy is good to. Okay, it's only good to 3 significant digits. So I'm gonna, this 9 is gonna be a 10. So that's gonna go up. So it's gonna be 10 times 10.0 times 10 to the 3. All right, and of course, that's not in scientific notation. So I'm gonna make that 1.00 times 10 to the, I decrease this number, increase that one, -2 moles per liter. Y'all with me? All right. Okay, and it is 350. What I'm going to have to do is I'll just do the rest of the problems on my own and then post that onto Blackboard. Okay. All right. Okay. Well, where do you want me to stop slide? Okay. All right. Okay, so yeah, let me take the roll. You guys don't have another class, so I think I'm okay with taking the roll after time. Okay, right, I'm still recording this, aren't I? Let me stop this. All right, so let's see, stop